Okay, final section of chapter 21. Again, it's one of the ideas you've covered at GCSE, but again, it doesn't happen on its own. So questions will tend to link the idea of radioactive decay, the type of decay, the probability of decay with a decay equation all through a different part of the question. So this bit is the mathematical bit, but you're going to have those other things as well. So in the end, these are all about practice. So this isn't really the why, but it does of course bring that idea of various things, bits and pieces together. So should we worry about radiation? Well, of course, everything that's unstable will become more stable. So if you have a substance that has a lot of radioactive isotopes, radioisotopes in it, well, it won't stay like that. So some of our sources, for example, our cobalt sources in particular, actually you could hold them in your hand without any risk because they decay so quickly. And because of that, they run out of energy quickly. So because of that, it means that the atoms have changed from an unstable isotope into a stable isotope, or a more stable isotope. Okay, so normally we will get a chain of several radiations happening. So you'll have for example, an alpha source given out to turn into a daughter Y, but it will also turn into, by giving out a different source, turn into a second daughter. So it will decay again. That will become a parent to that daughter, and so on. I don't know why they're not sons, but there we go. So yeah, decay is a chain of processes. And if we go back to our old chapter, our old section, our last section, what everything is doing, again to link it back to that graph, is that everything is working towards, by a chain of decays, working towards the area where it's most stable, somewhere in this region. Okay, so these elements, often transition elements, are our most stable ones. How do you get there? You will work towards it. So we'll move inwards from the ends, from the sides, towards this central region. And that is what makes it stable. But of course, you're not talking about individual particles when we're talking chemistry level. So we may have, 2 moles of substance. That's an awful lot of atoms. Statistically, some are going to decay, some have already decayed, some aren't going to decay for ages. Okay, because it's all about probability. So, to start off with, let's introduce 2 key terms. We're going to look at decay rates. It links in with half-life. It's based on half-life. It's calculated from half-life, to be precise. But this idea of decay depends on 2 key words. Random, like the version in gas particles, slightly different, and spontaneous, which is different, very, very different. So, chemistry, for example, chemical reactions are not spontaneous. Some things might spontaneously combust, but that's because the conditions are right. So, maybe there's more oxygen in the air. Maybe it's been put near a substance, so it will just combust. But however, for this, spontaneous radioactive substances are spontaneously decaying. We cannot do anything about it. As long as it is unstable, sooner or later, at some point it will decay. That's spontaneous. Okay, so these will just come apart. Random is kind of like, as I say, the gases. Which ones are going to decay? We don't know. Maybe it's going to be one corner first. Unlikely, because the probability is low. It's probably going to be spread out. Somewhere else is going to cause them. But there's not a chain reaction. We don't get that decay, so the next one decays, which decays the next one. We will just find that they will decay when they're ready, and that's it. So, when we're talking about how radioactive something is, we're actually talking about what comes out. Okay, whether it's a particle or gamma rays or neutrons, protons, you know, whatever it may be that's coming out. That will be very radioactive. Okay, this could be like a cobalt. Something that's less radioactive is still doing exactly the same thing, but doing it much more slowly. So every second it's throwing out less particles, which means that when we detect the particles coming out, we can tell what's happening inside. Because apart from gamma, basically, when particles come out, we know that one of the nuclei has decayed. So every particle that shoots out has come from a decayed nucleus. Gamma backs up the story, but it's a slightly different process, which is what we showed you last lesson. Oops. So, spontaneous and random, you do need to know those. You will need to be able to say that. They will often say, as their starter to a question, radioactive substances, or this substance decays randomly and spontaneously. What does random mean? Okay, so no predicting when it will happen or which nucleus. Okay, spontaneous, we can't do anything about it. Okay, it will just decay at the rate it wants to. Okay, so it is very random, and as I said, we'll do this with a really great experiment. We can look at these, but if you look at any of the things that you'll find, you never get a smooth curve. So unlike the billions of trillions of particles that are shooting out a capacitor as it discharges, radioactivity is much more random. Okay, so what you'll find is this is a very lumpy graph. Not like a capacitor, which is always smooth. However, the pattern is decay. It's still the same. Okay, so it's all dependent on how radioactive it is, how high its activity is. Okay, so we're going to need to bring in a constant. This is probably the best definition of the constant, the probability it was decay. It's basically, you can think of it as a fraction. So if you have a 50% chance, that's 1 out of every 2 will decay at any one moment, then that decay constant is a half. Simply that. Okay. Now when we say moment, the decay constant can change, not because it's not a constant, but it depends the time that it's measured in. So you'll have a certain decay constant if it's in seconds, which for us is our correct SI unit, but some things have a half-life of millions and millions of years, so seconds wouldn't be appropriate. So it could be decay rate for hours, minutes, seconds, microseconds. Some of them are really unstable, so they fall apart really quickly, or it could be millions of years. Okay, so you do need to make sure your unit is right. So let's go with the basics, and the basic is that if you have a lot of particles, a large number, then in that first chunk of time a lot of them will decay. So say half of them decay, it'll drop in a certain time to half the value. If you've only got half of them left that are unstable, they're obviously still there, it's just they're different atoms, then half of them decay in the next time, it'll drop to there. Half decay again in the next time, because you've got half as many, half of them will decay than decayed previously, etc, etc, so our rate changes. And what you'll end up with, there we go, is you'll end up with a lovely exponential curve, because the rate of change is proportional to the number that you've got. Now, before we move on, if you had a different activity, then you would end up with a different decay rate, and it might go really quickly. It gets a bit complicated if your parent decays slowly and the daughter decays quickly. So that kind of slowly changes. You're going to very quickly, that was quite easy because you'll very quickly build up Z, basically as fast as X is decaying. But if this decays quickly, but then this one decays slowly, then you're going to build up to this, change our x's into y's. Okay, so here is our unstable x, and that's changed into a stable y, but it might be on its way to changing to a z. Okay, the time it takes to get from that to that and that to that may be different, so it all gets a bit complicated. Which one depends on which one's decaying fastest. So in real life, again, a bit more complicated, but luckily we're just going to concentrate each step at a time, but just be aware of that. They can occasionally throw in those awkward ones. So, activity. Well, definition already got from when we did capacitors. dN by dt equals, is proportional to n. Excuse me, let me get rid of my parent's nucleus there and my alpha source. There we go. Now, notice, of course, it's not just rate of change, it's decaying. So it's a negative gradient. That is our gradient there. Okay, and simply, much simpler than GCSE, much simpler than capacitors. For our value, we're actually going to use our decay constant multiplied by the number, and that's it. So the derivation is much easier, but crucially, this gives us the equation that's on your data sheet, minus lambda n. Well, sorry, minus is not actually needed in this one, but lambda n equals a. So n is our radionuclides, in other words, number of nucleus, nuclei, S, nucleides, those number of nuclei that are left over that are unstable, and this is our activity. Okay, so that is strictly a number, whereas that is a rate. So this is what's happening inside the nucleus, this is what's flying out of the nucleus. Okay, so your activity, if you had 50 becquerels, as I've said here, then that's 50 decays every second, number per second, but it also means 50 particles that have shot out. So when we talk about radioactivity, we're talking about the rate of emission of alpha, betas, gammas, and other particles. Whereas what's happening inside is the activity depends on the number that you've got. So twice as many unstable ones, your activity will be twice as high. Okay, really important thing. So, worth pointing out, this slightly different from activity because this is your gradient. Whereas this is activity, which equals emissions or emission rate. Okay, so slightly different things, but exact equivalence between them. It's not just similar, they are exactly the same value. So, great, really useful. Don't overlook that equation. Again, it only has 3 variables, which means that generally from all our data sheet values, equations, if it's got 3 values, it's probably really important. So that's fundamental to what we're doing. Okay, so you will need to know that. However, it only becomes useful when we put it into a decay equation. So the number of nuclei you've got left after a certain time means that we have to consider how many have come out. So we're going to integrate dN by dt, equals minus lambda n. So that, in terms of what we want to get this, is we take our starting place and we're going to integrate it. So let's find out what happens to the numbers. So I'm going to take my my number across to the dn side, so that'll be 1 over n dn, and that's going to equal the rest of it happening on the other side with respect to t. So over time, what happens to, well, that only leaves my lambda, and I should say I'm going to keep the minus with that one, just make it a bit easier. And we're going to go from whatever our original source was, so just like capacitors and voltage and current and charge, we're going to, excuse me, I'll bring it into the screen, we're going to use n0 as our starting place, okay, and we're going to go to some value of n. So at our starting time, that was t equals 0, and then you're going to go on to some certain time afterwards. Okay. By now, you might well have done a bit more in maths. If not, go back to your capacitors thing. We can, derivation in capacitors, you'll find that we can work it out. That's differentiated is one of those key criteria, key notations, and it is a logarithm. It is a natural log. So we end up with natural log of n, subtract natural log of n naught. Okay, that is our square brackets. I'm going to do it in one step, so yes, log of n between those two values, and there's our two values, and that's going to equal t to the naught becomes t to the 1 divided by 1, so that's going to be minus lambda t minus 0. It doesn't matter, so you can't really have a negative 0. So crucially, useful version, instead of subtracting the logs, that's the same as the ratio of logs. So n over n naught equals, I said before, lambda t, minus lambda t, don't forget that, it's decaying, so we need a minus, or rearrange that and we can get the simple, get rid of that by exponential power of. So we end up with n equals n naught, after rearranging that bit as well, e to the minus lambda t. So that's our decay constant. That was the opposite of time constant, because that was a time, whereas this is how much it's dropping over time. So 1 over CR is equivalent to the lambda. I think this one's a bit easier, to be honest. So crucially as well, that equation tells us again what's happening to the number inside, but it also tells us about the activity. So because, or as, simply A is proportional to N, we end up with a bit like changing our X for charge or current or PD. We end up with the activity is the original activity, e to the minus lambda t. Okay, so again, two really important equations that we can use for whatever we're trying to do with it. It's worth pointing out we don't get a graph going up. Well, we do, but we'll just use common sense for that one. So if I go back to my sheet here, for example, I suppose what I should have is that is my number of radioactive red isotopes following that minus, following that curve there. Well, what are they changing into? If I simplify my equation, they're changing into y. So my value of y will eventually reach the original value of the x. In other words, they change from one into the other. Okay, so as the number of reds go down, the number of greens go up at exactly the same rate. So this, as I say on your graph, this is our daughter nuclide, there's our unstable parent. Okay, simple. That's kind of what we did with our derivation before. Now, in terms of this idea of half-life, that's a really powerful idea. I know you learnt it at GCSE because it was, you could read it off a graph, but don't you read it off a graph because that's rubbish. We need to do it in a better way. However, it has two versions and they're exact equivalent because again of this. So we could say how many of these two decay, or we could say how much this count decays. Exactly the same. So the half-life like the time constant of your capacitor, and you could do the half-life of a capacitor if you wanted. Tends to make more sense to use CR, but you could use exactly the same thinking as we're doing here. It's not the standard commercial approach. So we either talk about the activity or the number, should underline that as well, number of unstable atoms. So that's your N and that's your A. Ooh, excuse me, A. So how long it takes to drop to half of that original thing. Now, of course, as I said before, it will depend on your decay rate. So if you have a really large decay rate, i.e. the probability of decay is really large, then it's going to decay really quickly. Your half-life is really short. If you have a small decay rate, only 1 in a million every day will decay, then it's going to last for a lot of days before it decays. So half-life will be long. Okay, so that's a really kind of crucial little idea to just kind of get clear in your head. How do we work it out? Actually pretty easy. We've already done it up there or there. Okay, so if we wanted to work out the value mathematically, let's take the N version, but I could do activity. That's just going to equal a half. There we go. I'll put in brackets to make it obvious. So that's going to equal the right hand side of the equation, e to the minus lambda. I'm going to change my t to a t half is the symbol we use, capital T, because it's a value rather than continuous time, and time subscript half. I think fairly obvious that it's the half-life. So it's worth pointing out, again, for those who have done a bit more, I'll put in small brackets under here, that if we did 2 instead of half, so if we swap that upside down, you'd have e to the plus lambda t half. Okay, I don't know if you've picked up on that before, but that power tells you whether it's a fraction or not. If it's minus, it's a fraction. If it's plus, it's the opposite of the fraction. Hey ho. So, rearrange that anyway. What we'll find is if you want to make t half the subject to the equation, then I'm going to go for, it doesn't really matter, but I'm going to go for that one, so it's a bit easier. Log of 2 equals lambda t half. Okay, so useful equation, t half is log of 2 over lambda. Okay, really powerful equation, and again, when you look in your data sheet that I've just put down handy again, wherever we have, you'll see that right there. Okay, now they use a lowercase t. Not happy with that because that signifies changing things, but you've got all your bits and pieces there really. Last two equations, all of those we've just covered now. So crucial idea, visualize what they mean. Okay, because that's really helpful. Notice that version has the negative, that one doesn't, because that's how much, not the fact that it's going down. Because A isn't how much going down, that's a number of particles being emitted. That's your radiation, or how active your source is in the general phrase. So, really important. Why? Because that's usually the first step in your equations. Okay, they'll give you something that takes a certain amount of time, for example here, to decay. Is decay by half in 5 hours. So, if I use 5 hours, that will give me a decay rate in decays per hour. Okay, you do not need to change it into seconds, that just makes your numbers awkward, unless of course they give you some of the values in seconds, in which case you're either going to have to change them all to hours, or I would suggest change them all to seconds. It'll be a bit easier. So if you would have to just find this value and you weren't given it, you were given a graph, then again use your ideas from practical skills. That's your time constant. However, that would be a better value potentially, because that's 2 time constants, or find out that and that and then average them. Even better if you could go, in this case, from 25 to 12.5. If you could do it again, yeah, then again you can do it multiple times, average them. That will give you your best value. All right, so repeat it just like you would with any practical technique. But even better, if it was about data, then use the same technique as we did to get rid of this awkward shape of equation earlier on. Go back to subtracting and adding. It's always so much easier. So, using that idea of decay, okay, I should just point out try and point out, there we go. They are the same graph. Notice the same numbers, the same time constant. However, that's number of nuclei and that's activity. Okay, so in this case the values are the same. They might not be the same. I'm going to guess that the decay constant is 1 for these two graphs to link these two. So the numbers up here may be the same, but how long it takes to decay by half will be exactly the same. Okay, that could be percentage. If they're percentages, then obviously they're already ratioed for the same thing. So as I've said, down here, always try and do at least 2-3 half-lives. Okay, so at least. I'll highlight it because I know that people gloss over things. 2 to 3 half-lives. To find t half. Okay, so repeat. Even better though, as I said, is if we can use a straight line graph, that works so much better. So, running through, ideally, straight line graph, can we do that? Well, of course we can, because you've got to practice it with the calculations in capacitors. So, as I said, we had, again, doesn't matter if we're doing number or activity up the side, you'll get the same effect. So if I take number of unstable isotopes in your process, then what we can do is get rid of that. So if I do, if I log the whole lot, excuse me, wrong base log. So log to the base n, ln in other words, of n capital equals ln of n naught minus, well, let's say plus, plus whatever's here, which happens to be minus lambda t. Okay, and of course, looking at that, you can work things out. So where are our variables? Well, we have t and we have n. There are variables. Okay. So if I was to see how n depends on x, and I plot time on my x-axis, and I plot log of n on my y-axis, it will give me a straight line graph. I should say, or log of a and t, if you prefer. Let's put that underneath because you could have log of a equals, excuse me, log of a naught. I'll do it all in one thing here, minus lambda t. Okay. So if I plot that, I'll end up with a minus gradient where the gradient is multiplied by my x variable. Gradient equals minus lambda, and the intercept will be this remaining thing. Okay, so log of n naught, or depending what the graph is, of course, log of activity naught. Okay, so that's I'll stick with. Okay, that is on a log graph, but again, okay, to find that value, the original value, for example, the number of isotopes, number of elements, etc. within that, atoms within that element, maybe to then use Avogadro's number and do stuff like that, is not the value off the scale. You need to then do e to the log of n. naught. And if you do that, that will equal n naught. Okay, so don't fall into the trap of just going, that's my value for n naught. No, it's the log of n naught. Okay, and again, there's my graph, there's my t, that's my really large gradient. Obviously I would go to 0 line because that would be usually convenient, and that's going to be your minus lambda. Okay, super, same stuff, bit of revision. So I'll make that clear. There we go, on the y-axis, on the x-axis. So those are what happens over time to our radioactive source. How they're changing was the previous thing, and perhaps I didn't highlight enough at the time from this section. Make sure you know your way around the equations. Okay, so again, they will not say a proton changes into, they'll say neon 42 has decayed into, what is the decay given out? So it's going back to like, right, what have I lost and what have I gained? Okay, so it's quite easy to work out the numbers and then go, right, what is that source? What is that radiation? Okay, so you might work out that it is 0 nucleon number and +1, well that can only be a positron. Okay, an electron of charge +1, etc., etc. So that and that are always in the same question. Okay, it will involve, all of the questions in this chapter involve multiple stages. So go in to the notes in the workbook, okay, pick up on the bits that matter. I haven't put those in because I need you to have a form that works for you. It doesn't matter, there's no specific answers to those, I should say. But when you get into your modes of decay and so on, you're starting to think about what it's turning into. Again, this is a fairly typical kind of question. So this one is one that is split, plus a bit comes out, etc., etc. So you can work out what's going on. That one's slightly different actually. We've got difficult processes. So this one, I should say, isn't question 20. There isn't a question 20, that's actually the question to go with that information. More complex things, but again, it's just going, right, what's happening, and it breaks it down into steps. But loads and loads and loads of questions about what it makes and how much is left after a certain time. So get a load of practice with this chapter. It's far more common than particle physics. Okay, just practice, 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 check your answers, and then do as much as you can on Isaac physics, potentially on carousel, but Isaac physics is the maths of this, and that's where most people get a little bit stuck. It's not as hard as gases, and the exponentials not as awkward, I think, as the capacitors. Okay, so practice and practice, guys.